Okay, so very quickly looking at this together, what type of series is this? It's an alternating series. It's got a -1, and it's either to the n plus 1, or n minus 1. Those are the typical ones. And then, of course, we had the covert alternator, cosine of pi n. We saw that the other day. So if you want to determine what the sum is, again, you can always approximate it using a partial sum. And this one says, find the first 6 terms. So without listing them by hand, again, you can go to the calculator here, and if you hit alpha window, it's number 2, summation. And we'll go from n equals, which we'll just use x, equals 1. And the sum of the first 6 terms, we'll just put that as 6 instead of infinity. And now to type this in here, I'll use my horizontal division bar. Parentheses -1 raised to the x minus 1 power. So again, it's going to treat x as a whole number because we're in sigma notation, not a real number. And then x factorial, x, and then if you hit math, click to the left to probability or right, it's number 4. And then if you hit enter, you'll get this number here. So I'm going to label that as s subscript 6 is equal to 0.631. And then I'm going to store that as alpha a. Okay, so there you go. I'll store it as a right there as well. So that's the sum of the first 6 terms. Now, based upon the alternating series test, which we did last Friday, would you suspect that this series converges or diverges? Converges. Yeah, it does pretty easily, actually. If you look at the alternator and you realize it's there, then the test says, okay, get rid of the alternator. Does 1 over n factorial go to 0? It does. Very, very, very rapidly. And do the terms get monotonically smaller as n increases? Yes, they do. And therefore, by the alternating series test, this series converges. The next idea we had was, is it absolutely convergent or conditionally convergent? That test is determined by, all right, if you take the absolute value of the rule of sequence, that is, if you got rid of the alternator, and this problem was just 1 over n factorial with no alternator, would it converge or diverge? Well, your suspicion should be what? It still converges, even without the alternator's help, because n factorial grows faster than exponential. And remember, exponentials go to 0 fast enough to converge. So anything that goes to 0 faster than that should also converge. We'll have to decide that for sure, though, with the ratio test, which is coming up. So this one we would say is absolutely convergent. It converges with the alternator and without the alternator. Having the alternator there, remember, only subtracts every other term and makes the sum smaller. Okay, now this, what we're going to do next, is on the AP exam. There is a way, if you add up the first 6 terms, to decide how close that partial sum is to the actual sum. And it's called the alternating series remainder. And it's a lot easier than the integral test remainder. The integral, remember, said that the error is going to be within the integral from 6 to infinity. If you added up the first 7 terms, it would be within the integral from 7 to infinity. But the alternating series remainder, or error bound, as they're also called, is this simple. If you use 6 terms to add up the partial sum, the error, or the upper bound, is going to be within the absolute value of the first unused term. So we would call that R sub 6. That's the remainder using 6 terms. It's going to be the absolute value of the 7th term. It's always the absolute value of the first unused term. So let's figure out what that's going to be. What is the absolute value of a sub 7? Well, when you take the absolute value, you don't need the alternator, do you? Because it's just plus or minus. So it's just going to be 1 over 7 factorial. Right? That would be the 7th term. The 6th term was 6 factorial. Now, if you want to get an interval in which the actual sum has to live, then here's what you could say. S has to be inside the interval of, in this case, it'll be a minus 1 over 7 factorial for a lower bound, and a plus 1 over 7 factorial for an upper bound. For the integral test, it was a little bit different. For the integral test, since our dogs had to cuss in prison, all the terms were decreasing, continuous, and positive, our lower bound could have just been the partial sum. But because this alternates, we're adding and then subtracting, and adding and then subtracting. So every other term, the sum's going to get a little bit bigger and a little bit smaller. So to get a safe lower bound for the sum, you actually have to subtract the remainder, and to get a safe upper bound, you have to add it. Okay. Whereas for the integral, it's just the lower bound and then the lower bound plus the remainder. And because I stored it as a, here's what we could do now. We could just say it's going to be, for the lower bound, alpha a minus 1 divided by 7 factorial, which is math probability 4. And there's the lower bound. And then to get the upper bound, I could just recall that and come over here and put plus. And then this could be a question. It could ask you as a multiple choice, which of the following values could be the sum for this alternating series? And they'll give you a bunch of different answer choices, and only one of them would fall between 0.631 and 0.632. So could 0.65 be the sum? No. Could 0.62 be the sum? No. But could 0.6319 be the sum? Yes, certainly. Okay? So that's all you'd have to do, is figure out what the upper and lower bounds are. Now let's see what the actual sum more than likely is. We can kind of use the calculator now to do the heavy lifting for us. They didn't have this luxury back in the day, remember? So computing these terms by hand was a very arduous task. So that's why they wanted to have these error bounds. Okay? Adding up the first 6 terms by hand is no mean feat. So they might even want to stop after the sum of the first 3 terms. But then they also then wanted to figure out, okay, well, how close am I to the actual sum? Here now at the calculator, we could type in, I don't know, a 12. Because this converges so rapidly, this might actually approach the actual sum pretty quickly. So does 0.63212 live between 0.6317 and 0.6321? Yeah, it should be in there somewhere. It is. Okay, so there's the idea. If you use the first 6 terms for the partial sum, then the the alternating series remainder, also called the error bound, is going to be the absolute value of the first unused term. All right. Here's kind of a slight twist on that. Example 19. It says approximate the sum of this guy here so that the error is less than 0.001. All right. How do you think we'd go about doing this? First of all, is it an alternating series? Yeah. Does it converge? Yes. Absolutely or conditionally? Absolutely, it converts absolutely. Yeah, because without the alternator, it's going to be a convergent P series. So this then converges absolutely. I want to then figure out the sum so that it is within 1/100,000th of the actual answer. So how am I going to figure that out? First of all, remember the remainder is going to be the absolute value of the first unused term. So all I have to do is start figuring out what some of the terms are, and the first time I get to a number that's less than 0.001, I'll say that's the first term that I don't want to use, right? And I don't have to worry about the alternator. So let's see. If I let n equals 1, then that's going to be 1 over 1 to the 4th, which is 1. Is 1 less than 1,000th? No. How about when n equals 2? That's 1 over 2 to the 4th. That's what? 16th? Is 1/16th less than 1,000? No. Let's go ahead and do this on the calculator. When n is 3, it's going to be 1 divided by 3 to the 4th. Is that less than 1,000th? No. So let's try another one. 1 divided by 4 to the 4th. Is that less than 1,000th? No, that's 3,000. Let's try it again then. 1 divided by 5 to the 4th. So trial and error is not a bad way to go. Is that less than 1,000? Not quite. Well, I'm getting close. 1 divided by 6 to the 4th. Is that less than 1,000? That's 0.0007, right? If you move it 4 decimals back to the left, it's 0.0007. That is less than 1,000, okay? So it turned out that the 6th term was the first term that was less than 1,000. So to get a sum then, I'm going to use how many terms? If the 6th term is going to be the first unused, then I'm going to add up the first 5 terms. Yeah. So S sub 5 would be the sum that is the first sum that's within 1,000. Okay? Everything past that is also going to be within 1,000, but that would be the very smallest sum that's within 1,000. So how would you find S sub 5 then? Then you could just plug this into the calculator using the sigma notation. Okay? So the alternating series remainder is pretty easy. Just make sure you're taking the absolute value of it. It's the first unused term. And if you're looking for an interval, make sure you subtract to get the lower bound, add to get the upper bound. All right, the last test that's going to be on the AP exam is the ratio test. But I always throw the root test in there as well because it's very, very similar. Now, the ratio test is going to be a very important test because when we get into the domains of power series, which is interval and radius of convergence, we're going to use the ratio test primarily. So here's what the ratio test says. Let us have an infinite series with a rule of sequence being a sub n, non-zero terms. Okay? Here's what it says. It's a two-way test. The series then is going to converge when the limit as n goes to infinity, kind of like the limit comparison test, of the absolute value of the n plus first term divided by the nth term is less than 1. So unlike the limit comparison test where we have to find our own series and we bring it into the fold, this one we're just using the one they give us. We're going to have to figure out what the n plus first term is, and I'll show you that here in a second. We divide it by the nth term. If that's less than 1, the series will converge. The idea being that as we go further down the line, the one that precedes is bigger than the one that follows. Anytime the one that precedes is bigger than the one that follows, it's going to 0 fast enough for the series to converge. If the ratio that you just computed is bigger than 1, then the given series diverges. And kind of like the first derivative test, unfortunately, it is inconclusive, though, if the ratio equals 1. All right? In which case, there's probably another test that works. So much like the geometric series, we're looking for a ratio to be small, smaller than 1. Now, when do we use the ratio test? How are we going to know when to use it? Geometric series are pretty easy to spot. P-series are pretty easy to spot. We're going to use the ratio test for things that grow very, very rapidly. That's kind of on the upper end of the growth spectrum. So anything that has factorials in it typically is a ratio test, and or anything that has exponentials in it, like geometric. Any powers of n or any factorials are very well suited for ratio tests. So let's look at example A. You have an infinite series. It's 2 to the n over n factorial. Let's do the nth term test for divergence first. Always do that first. Which one goes faster? Exponential, essentially, in the top, or factorial in the bottom? Factorial. So the terms do eventually go to 0. They do go to 0. So which means that it has a chance to converge. This is not a geometric series because the n factorial ruins it. It's not a power series, so we can't use that. We can't really compare it to anything then because it doesn't look like a geometric or a P series. But it does have exponential and factorials. So this is a good candidate for ratio tests. Now, before we do that, I always like to see intuition at its best. What do you think? This one converges or diverges? You think it converges? N factorial, you think, then overpowers the numerator eventually and pulls it to 0 fast enough so the sum converges? We'll see. We'll see if you're right. Here's how you do the ratio test. You take the limit as n goes to infinity. The way that you're going to get the n plus first term is very simple. You just replace n with n plus 1. So you get 2 to the n plus first all over the quantity n plus 1 factorial. Okay, and we're going to take the absolute value. Divided by the nth term, which is just the rule of sequence. So it's just over 2 to the n over n factorial. So that's how you set it up. The n plus first term, just replace all the n's with n plus 1 and divide it by the given rule of sequence. Now from here, there's going to be a little bit of, housekeeping. Stay, change, flip, essentially. And if you know that it's going to be stay, change, flip in the next line, you can actually skip the first step and go straight to that line right there. In other words, instead of dividing by the nth term, multiply by the reciprocal of the nth term. Saves a little bit of writing. Now, here's what we're going to do. We're going to simplify. And these always simplify down pretty nicely. We have, first of all, 2 to the n plus 1 in the top and 2 to the n in the bottom. So we have one more factor of 2 to the n in the numerator. So all of the 2 to the n's will divide out, leaving just a 2 to the first power. Yeah, in other words, 2 to the n plus 1 is really 2 times 2 to the n. And your 2 to the n's will divide out. So you're left with just a 2 in the top, and then these divide away. And then n over n plus 1 factorial. Here's how you divide those out. Which one's larger, n or n plus 1? N plus 1. So in the bottom, you're going to start with the larger one, n plus 1, and then start writing it in descending order until you hit this one. Well, that'd be the very next one, right? N factorial. So what's going to happen with your n factorials? Now they divide out, and we're left with an n plus 1. And now we have the limit as n goes to infinity of 2 over n plus 1. What's that going to equal? 0. Is 0 less than 1? Sure it is. So the series does what? Converges, yeah, by the ratio test. Yeah, all right, your intuition was correct. If the bottom is factorial and the numerator is anything smaller than factorial, because that would be the next smallest, it's going to converge, the series is. So intuition goes a long way. Yeah. It was there in the beginning. This one? Oh, yeah. So I did this, and then it's divided by that. I just multiplied by its reciprocal. On the red one. Yeah. So 2 to the, how did the 2 get there? Well, I multiply straight across. Yeah, yeah. So there's a dot, so we can multiply straight across. So really, at this point, you can connect that right there. And it becomes the numerator. One numerator, one denominator. So your factorials will always divide out, and your powers of whatever will always divide out. Okay? So this is like 2 times 2 to the n, and the bottom is like n plus 1 times n factorial. So these n factorials will divide out, leaving an n plus 1, and these 2's divide out, leaving just a 2. Okay? Yeah, so the algebra, you'll get used to the algebra. It's kind of fun, but if you get the hang of it, doing a couple of problems, you'll have it down. All right, this one here. It's an infinite series. Nth term test for divergence. We'll tell you what. Do the terms go to 0? I think it diverges, right? 3 to the n, first of all, grows faster than 2 to the n. So if that were the case, then it would diverge by the nth term test. But it also has another helper in the numerator, n squared, which makes it what? Grow even faster. So this thing can actually diverge by the nth term test because the limit as n goes to infinity of that does not equal 0. That's all you have to say. It doesn't equal 0. Now, if you want, you could prove that with the ratio test. Do you want to prove it with the ratio test? You might as well. It's good practice with the algebra. We should get the same result, though. All right, so here we go. The limit as n goes to infinity of the absolute value. The n plus first term is going to be the quantity n plus 1 squared times 3 to the n plus 1, which is n plus 2, all over 2 to the n plus 1. So every n becomes n plus 1. And now instead of dividing by the nth term, I'm going to multiply by its reciprocal, 2 to the n over n squared times 3 to the n plus 1. So n plus first divided by n, state change flip. We're at this step right here. Now really the absolute values, you could drop them at this point if you want. They're really only there in case you have like an alternator. You can just drop the alternator. All right, let's do the exponentials first. You have 2 to the n on the top and 2 to the n plus 1 on the bottom. So you're left with a 2 where? In the bottom. There's just one extra 2 in the bottom. So now if you want to divide those out, that's good. And then very similar with the 3's, 3 to the n plus 2 and 3 to the n plus 1, we have one more 3 in the top than the bottom. See that? We have n plus 2 of them up here, n plus 1 of them down there, so we're left with just the 3 in the top. Yeah, you could actually subtract, right? That's what we're doing. N plus 2 minus n minus 1. Yeah, if it had been like 3n plus 3, then it would be 3 squared. And now the n's don't really divide out, so we're just left with n plus 1 squared all over n squared. It's really only the factorials and the exponentials that divide out kind of nicely. But I think we're pretty good here. We could still figure it out. If you were to expand this, your leading term in the top would be 3n squared. And in the bottom, your leading coefficient is 2 on the n squared. So you're going to have an n squared over n squared, which means leading coefficient over leading coefficient. This would equal 3 halves. Is 3 halves less than 1? No. Is it equal to 1? No. It's greater than 1, so the series diverges. But now it diverges by the ratio test, not the nth term test. Doesn't matter what test you use. There's going to be sometimes more than one. They should give you the same conclusion. The ratio test pretty much works except when the ratio is 1. Then you got to try another test. All right. What about this one? It diverges by what? Nth term test, right? So you would just say the limit as n goes to infinity of n plus 1 over 3 to the n. All you have to do is say does not equal 0. So the series diverges. And again, if you wanted to do the ratio test will give you the same conclusion. And it would be a good candidate here because you do have, again, factorials and or exponentials. Now the ratio test is we'll be using it a lot in the next two sections. The last one here is the root test. And again, this one's on the BC exam, but as of yet, maybe we'll add it someday. But it's almost identical to the ratio test, okay? But this one works well if you have like powers of n, almost like geometric series. If you just have an entire quantity raised to the nth power. It says if you take the limit as n goes to infinity of the nth root, that's why it's called the root test, of the absolute value, then if it's less than 1, it converges. If it's greater than 1, it diverges. And if it's equal to 1, it's inconclusive. So really kind of the same conclusion as the ratio test. But instead of taking the n plus first over the n, we're just taking the nth root of it. So it's kind of like a freebie that we get. So if you look at this one here, it's an infinite series. What happens to the terms as n goes to infinity? They do go to 0. You have exponential on the top, pretty impressive, but the bottom is the Aleph function, n to the n. And that's the king or queen of all growth. So the terms do go to 0. So this has a chance at converging. And of course, your intuition would tell you, does n to the n overpower e to the 2n enough to make it go to 0 fast enough? You would think yes. Well, in this case, it's not. We can't write it as a geometric. I can write that as e squared over n all to the nth power, right? That would be the same because they're both powers of n. I can pull the power of n, but e squared over n is not going to be geometric because n is still a variable. So it doesn't quite work. But we could use the root test. Let's try the root test. The limit as n goes to infinity of the nth root of the absolute value of, I'm going to go ahead and write that again as e squared over n to the nth power. So again, this works well for things you can write as powers of n. Well, the nth root of something to the n is just itself. So this would be the limit as n goes to infinity of the absolute value of e squared over n. And now, of course, where does that go to? It goes to 0. And 0 is less than 1. Therefore, the series does converge. So for the most part, if you have an exponential in the denominator and something that grows smaller than exponential in the top, then the series should converge because it goes faster, and it works its way then up as well. If you have a factorial in the bottom, then anything smaller than factorial in the top will make it go to 0 fast enough to converge, and then you work up to the final layer here. If you have the Aleph function, then anything smaller will converge. This one, what would you do on this one? It's not quite geometric, but it's something all to the nth power. If you take the nth root of it, what's the nth root of all that to the nth? It's this. And what would be the limit then of 3n plus 4 over 2n as n goes to infinity? 3 halves. Is 3 halves greater than 1? Yeah. So this thing diverges by the root test, but could you also kind of make the same argument by the nth term test? Yeah, you could, because the limit as n goes to infinity on the inside is 3 halves, and 3 halves to the infinite power times 1.5 times 1.5 times 1.5, that gets infinitely large. So it can also diverge by the nth term test. Okay, so really the important ones are the geometric series, and that's less than 1. It's exponential, right? Because that one we can also find the sum. It's the first term over 1 minus r. P-series are also important. They're like the P-series from the integrals. If the power in the denominator is greater than 1, it's going to converge. Otherwise, it diverges. Then you got your limit comparison test. And then you have the alternating series test and the ratio test. So let's look at example 22. I don't think I'm going to do all the tests. Oh, we also had the integral test. Sorry, dogs cussing in prison. Let's just use our intuition here and maybe name the test. What do you think on this one? These are all, by the way, infinite series because they all have infinity up there. Converges or diverges? Diverges by the nth term test. We'll start over with example 22 after lunch. Pretend we didn't even do that. It was a nice clean break on the previous example. Have a great lunch.